Today we're going to have 1, 2, 3, 4, 5 presentations. We have Juliana, Juliana and Finn and Pete. We have Kelsey, Justin, and we have John and Arthur, and Bruce over there. All right. And then next time we'll have Aaron and Stephen, Emerson and Eric, and Omid and Mohammed, Gus, Fernando, sorry, Mason and Price. Okay, that's a good one. 1, 2, 3, 4. Okay, that's all. So we're going to grade by the amount of effort, originality, execution, and complexity, and the presentation. Okay. And thanks for coming all today.
So, hello everyone. Today I'll be presenting one of my recent works, which is on transformer-based model-predictive path integral control. So MPC, as we know, has been a powerful framework for optimal control, and they have been widely used for many applications. However, they are computationally slow whenever we have a general complex high-dimensional nonlinear system. Furthermore, when we have nonlinear constraint, MPC can be quite computationally expensive. In recent years, model predictive path integral control, which is a sampling-based control technique, has been a popular choice and has been implemented for a wide range of applications. So the basic idea I'll discuss in detail behind MPPI, but the main logic is to sample the trajectories and then to weight these trajectories to modify the control sequence. But the main challenges with MPPI is sample efficiency. So usually we need a large number of sample trajectories, so that we can get an optimal control sequence. Second is because we have to have a large number of samples, the computational cost is high. Finally, the optimal solution depends on the mean. So if you have a more informed mean, then you can be sample efficient. So what we are proposing here is we are using transformers to be able to get an informed mean initialization for this MPPI. So consider a system given by equation 1. It's a discrete nonlinear system. It doesn't have to be smooth. It's just a nonlinear state transition function. And WK is like a perturbed control input taken from a normal distribution with mean UK and covariance sigma U. The optimization problem is to minimize the expected cost of JW, where Q is the probability PDF of UK, PDF of WK, and you have a running cost SK, which does not have to be smooth. You have a state transition function, which again does not have to be smooth, and H, and the nonlinear constraint H, which also does not have to be smooth, subject to input constraints. So the MPP algorithm is inspired from stochastic optimal control. I'll not go into much detail about the details of this concept, but let me just briefly introduce what is MPPI, like the background of MPPI. So we first define a free energy, which is a function of the cost, the PDF of the noise variable. Then you have x0, which is the initial state, and lambda is just a positive constant, which is given by the term right hand side. Then the optimal control input distribution, which is given by Q star, can be derived from this expression. The derivation is lengthy, but as you can see, there is this cost function J, there is this lambda parameter, and there is this probability function, which is the noise of the control signal. Then you can sample based on this distribution given by Q star W, which is given by this expression. So coming to the implementation, the optimal control is given by the expected value of nu of W into Wi. So Wi is the control sequence, which is the sample control sequence, noisy sample control sequence, and nu is the weighting function given by this expression. And eta is such that the PDF like the integration of PDF is equal to 1, and the final control computation is given by the final expression here, where we have the weight nu k and we have the noisy term epsilon ik, where k is the kth sample. So as I mentioned, whenever you're sampling, you can sample the trajectories in the high cost regions. So you're not sample efficient. So you might be losing out some parts of low cost trajectories also. Requires high number of samples. Even though it requires large number of samples, it can be parallelized using GPU. But still, again, it requires a large number of samples. And you have high computational burdens because of this sampling. Because for every sample, you have to evaluate the cost JW, which can be expensive. So what we basically do is we leverage transformer to initialize the mean. So this mean is such that you need lower number of sample for sampling the trajectories around that mean. And this mean is like then close to optimal control sequence, but not the optimal one. Again, what we show in the result section is it requires lower number of samples. And since we already are starting from the mean control sequence, the acceleration is quick to the optimal control sequence with fewer number of samples. So this is like a rough example of the difference between MPPI and the transformer MPPI. So what you can see here in this figure is whenever you have state xk, and suppose you are going through the entire horizon with that control sequence, the next control sequence you are initializing the previous control sequence. So you're using the previous control sequence as the new mean for the MPPI. That is usually the literature. What we're basically doing is we're using transformer to initialize a better mean, not the mean which is from the previous control sequence. And this gives significantly lower number of samples as well as lower cost. So this is the proposed architecture. This is a typical feedback loop. So everyone is aware of this. But instead of what we are doing is we are replacing it with a learned model, and that is used in the MPP algorithm. So this is what we have learned. So the input is the encoded state, which consists of the parameters of the problem as well as the environment information, which can be the location of the obstacles, etc. And that is to the encoder. For the decoder, we are giving the optimal control sequence, but a shifted target sequence, which is decoded in UDEC. I'm not describing the equations here. And this is got using the MPP algorithm. So we are doing data generation using MPP algorithm, and we are running it for a long number of time. So we are getting for data collection, we are using the original MPP algorithm. And the predictions are just the optimal control sequences. This is the encoder and the decoder block, which is present here. So I'll not go into detail. Data collection, as I mentioned, we are using MPPI. We are training transformer on this data set. And we are using teacher forcing strategy. Basically, it means that, okay, you're using as the input, you're using the optimal control sequence from the MPPI, like instead of being it as the output. So that is basically teacher forcing strategy. Again, to quickly mention what is transform MPPI. Predict mean control sequence based on the parameters of your problem using transformer. Sample control sequences around the predicted mean. Evaluate the cost and update the control sequence. So again, this is just the formal description of the pseudocode. But again, it's the same. So from line 6 to line 11, we are sampling k sample, like k trajectories, where we are sampling the control noise in equation in line 7. And we already predicted the mean control sequence in 5 using the trained transform model pi theta. And then we are calculating the weights nu k for each trajectory using the equation which is previously described, and then we update the control sequence, and that is applied to the system. Now coming to the simulation, we consider two problems. One is the collision avoidance in a 2D environment where we consider dynamic obstacles. The second is an autonomous racing where we take the circuit track from the Japan Racing Challenge, and which consists of static as well as dynamic obstacles. The metrics are again the overall average cost with samples, then the sample efficiency, and what is the overall cost in presence of dynamic obstacles. So this is a typical representative, like typical example you can see, where original MPPI is giving collision-free trajectory, but it is not optimal because it's taking a curved area, whereas transformer MPPI is just going straight and efficiently avoiding collision with the obstacles. So coming to the results, as you can see, the red one is the transformer MPPI and the blue one is the original MPPI, and this is a bar plot, box plot. So the cost is significantly less with the as we increase the number of samples. That is the first observation. The second observation is when we consider the episodes over which we are taking the average, you can see consistently the transformer MPA is lower than the blue curve, which is a good thing. And if you see for the again the average number of steps, which is representative of the time it takes to reach to the goal, is also less. But for higher number of samples, transformer MPPI performs poorly, or in other words, there is no much difference for high number of samples because you have more number of samples. So it does not make more sense to initialize a informed mean. So there is a lot of benefit when you have 50 samples. Again, this is for the episode. What are the number of steps which is required? You can see it is significantly less, where there's one, however there's one outlier. Now coming to the dynamic obstacle. So basically for dynamic obstacle, we have 15 obstacles and we give a velocity range where the every obstacle is moved randomly in random direction with a particular speed. So 0 means none of the obstacles are moving and 15 means all the obstacles are moving. As you can see, the cost is always less whenever for if you move any number of dynamic obstacles. So next is the autonomous racing. This circuit track is taken from the Japan Racing Track Challenge. So it's more realistic. We have certain obstacles, as you can see here, circle obstacles. And the task is to go, is to make the racing car track the lane it has to go, but it has to also avoid the collisions. And it has to have a lower cost. This is also a representative figure. As you can see, the transformer MPPI has a lower cost. And coming to the results, here are the results. We observed significant reduction in the cost for lower number of samples. But if the number of samples are high, we don't observe any much differences in the cost. Similarly, this is for over the episode. There is consistently reduction in the cost. And even for the dynamic obstacle, where the obstacles are moving. So there are totally 50 obstacles, and all for even if all are moving, we have consistently lower cost. So that's all. And to conclude, what we're doing is we're initializing mean using transformer, which reduces the samples required as well as the computational cost. The future work can be as follows. One is, of course, to deploy it on physical robotic systems like legged robots or humanoid to see the efficiency. Second is to extend to multi-agent systems. Third one, I didn't mention here, but one can also use transformer to have an informed initialization for the covariance. So we are initializing the mean also, but if we have, if we can initialize the covariance also efficiently, then that is a great thing. People have some works where they have derived, okay, what can be a better covariance depending on the cost function. But instead of that, one can use again neural network this transformer architecture to have a better, so we can get more better results. Yeah, that's all.
Hi, I'm Juliana. This is Finn, and we're presenting our final project, which is learning on system fusion for able-bodied motion prediction. So we're just going to do some background real quick to recap y'all on our project. So some of the motivation behind this is gait labs are restricted and expensive environments, so they can't study a lot of different movements. We want to study biomechanics using a sparse mobile set of sensors. We want to specifically capture a wide variety of natural movements, specifically movements that current prostheses wouldn't be able to predict. We want to move away from sort of mode-dependent predictions and do something that would help people in real life. Sort of like how you would be in a grocery store if you have a cart coming out you have to avoid, or you have an item you want to pick up. Those are things that are pretty hard to predict. So our main question is, what continuous biomechanically valuable signals can we recover from our sensors? And to recap, our sensors are the X sensor, insole capacitive pressure sensor, and then an ultrasound placed transversely on the right quadruped. And the signals we're trying to recover from that are the joint angles of the right leg and then the whole body angular momentum.
So like we talked about last time, our data collection was for 3 subjects. We had them do 30 minutes of overground walking, which is pictured in here. That included level ground, stairs, and ramps. We then had a 10-minute unstructured trial, kind of trying to get at that grocery store environment. So that included like sit-to-stand, lunges, even kicking a soccer ball. And then we had the 30-minute treadmill trial. We're just trying to bulk up our data set. However, that is unlabeled because, as we've been talking about so much, ours was special because we were trying to do self-supervised learning. So using that treadmill data set as well as the other ones, we do self-supervised learning over all of it. Then we take those model weights, pass them over to a very slightly different model where we shift the labels forward 2 frames, which converts to about 26 milliseconds. The purpose of that is that if we're looking towards prosthesis control, there's a lot of delays involved in that, and you want that to be as snappy as possible, so if we can get toward future prediction, it's very valuable for us. And then finally, we go to our last little network there, where we train on labeled, overground, and unstructured trials.
And then typically in biomechanics, you'll see a lot of models like this trained within subjects and then across subjects. So we did the same thing. We're going to go over some individual subject results, and then Finn will present the more combined results. So first up, our subject 1. Those GIFs, the SSL results, is our autoencoder results. So we feed it that image, we put it down to 128 dimension, and then we make it go back up, and we got pretty good results. You can see some blurring effect, but all in all, we were happy with those results. And then on to our labeled results, the more interesting part of this. So you can see that it handled walking pretty well. It matched it pretty well. And then what's really promising for us here is the sit to stand was a movement that was not in our training set. So that was an entirely new movement to it. It had no idea what that was beforehand, and it did it pretty well. So a theme you're going to see is that human data and our markerless motion capture data are unreliable. They're not great. So we don't really know what happened with this angular momentum. That's just what the machine spit out. We had a lot of errors with that. So we're going to ignore that for now. For the next subject, again, the autoencoder results were really good, even with a different ultrasound and different X sensor pattern. And again, I'm going to talk about our markerless motion capture system. In the predicted, you'll see those big drop-offs. So in our post-processing, there were times that the motion capture would lose track of a joint. It would just kind of take it away. And when it did that, it put a really negative value for the joint angles. We thought we took all those out. We think we did. We think another error that happens is there's a bug, something happened, and it just spits out another randomly negative number. So we think in this subject's training data, we just missed some of those bad angles. And so it's predicting stuff based off some bad data, even if this testing data looks good. But as you can see, it's still responding to our input signals in a pretty good way compared to the output. And even with that sit to stand, it's still, if you took out those data anomalies, we think it would still respond in a good way to a task agnostic thing. Again, the angular momentum, we just don't think that that's a very reliable calculation from this system. So again, we're going to kind of ignore that for now. And then our last subject. Again, walking looks pretty good, to be honest. And then the sit to stand. So the magnitude is off, but you still see that that response from our input in the correct shape. And so even though the magnitude's off, this is still a pretty good indicator for the signal we want, which is those angles. So it's still a valuable recovery for us. And again, that angular momentum is just not great.
Cool. So then we looked at combining the data sets a little bit. So going from the top row, that was the one you were just shown, but for subject one. Below that, we do self-supervised learning on all three subjects, but we only do the labeled training for within that one subject. And then the last one is self-supervised on all three and labeled on subjects 1 and 3. We drop out subject 2 there because, like we talked about, the data was quite bad, which is also visible in the training loss. Subject 2 is the red one, much higher. The good things here is that there's a marginal but noticeable improvement as we expand the self-supervised set. You can see some of the particular spots, I can't gesture, but where it really overshoots, those get brought in a little bit. However, when we try to do labeled training across multiple subjects, things go bad very quickly, which is something that we've observed before. This is possibly just a result of not having enough subjects. If we had tens and hundreds of people, it might wash out some of these subject differences, but with only 2 people, the network gets confused. And at the very beginning, we said we were going to do hip, knee, and ankle. We've only been talking about the hip for brevity, but just to finally show, we did also do the other angles. And so here, the blue line is the prediction just within one subject. And then the green is with additional self-supervised learning, but still labeled training within one subject, because that had the best results. And so here you can kind of clearly see that these big peaks get brought in, which is good for us. And we're generally pretty happy, as shaky as some of these signals look, like the ankle. Again, the system that we're working with just gives bad data sometimes, and a big theme of this project was, how do we fix that? So some things we got away from this, and looking to the future, it generally worked well. We were able to recover the joint angles. We think from like a dynamics of systems perspective, H was just not in the signals that we had. That's why it had such a hard time recovering it, let alone the fact that Thea sometimes gave bad values. We were really happy with the task independence, but the subject independence was, unfortunate. And although the SSL gave limited improvements at this stage, now that we've built this architecture and we continue to collect data, we're really excited that it will continue to pay dividends. And finally, this project is done in terms of the class, but it's not for us. So towards the future, we're going to move into like a TCN or transformer to incorporate the context of walking.
So my name is Pete, and I'll be presenting on reinforcement learning and vision games. So again, this motivation comes from spacecraft. So as we know, spacecraft is used to utilize vision sensors for a variety of RPO scenarios, mainly for passive and friendly competitor, or passive targets and friendly competitors. This comes up in ISAM, debris removal, and formation flag. What we're interested in is extending this capability to uncooperative adversarial scenarios. So in other words, this project is more interested in using reinforcement learning, again, to develop a control policy that will maintain targeting on some adversarial target that's trying to get out of the camera.
And that's what it looks like. First one, try to keep the camera target. If he leaves, I want the camera to be on him. We don't want it to go away. And the reason that is because if we have this kind of set of information where this is the adversary state, we usually can't get this without having some good visibility in the space scenario. So having visibility of the spacecraft and then doing some, you could say, you could use key point regression and then do some relative nav filtering to get that adversarial state. But when you don't have it, we want a policy that can still keep it in target in order to get this target state to have like this full suite of control. But this project only focuses on this like set here. Again. So the first thing we did, this first push, was creating a gymnasium environment to, train these things. And when we made this, it was we were going to assume that these agents were operating in some closed operational area. So this would be some region of interest, could be around the satellite, and some region of space that's interesting. And then in this operating region, we'd have 2 spacecraft, a target spacecraft that's operating in that region, knowing that we're there and trying to stay out of view, and then us, who is trying to keep them in view and keep them in this detection code. And then this is what we came up with, this is what we showed at the first update, was that we made this gym environment and we gave a bunch of flags to do the different training we'll talk about later, as well as making it modular to take in different dynamics and reward functions, and then rendering it so we can have a visualization of it. So the first thing we did in that first update was we did self-play for asymmetric games. So we have self-play, but we have two different policies. We have a target policy that's trying to do something and an agent policy that's trying to do something else. And inspired by this YouTube channel, again, AI Warehouse, we decided to use self-play. And that's essentially where we have two policies in this environment. We train the target policy a little bit, and we train the agent policy a little bit. We keep swapping that in order to get some policies to play this game using privilege information. And then, as we showed again, we showed that we could do this and that we had some good policies that could play this game with the privilege information. But we showed it to R5, and then this took a long time to actually make, but I did 100 rotations, and we get this kind of shape. And as you can see, it's a very noisy shape. It's not really smooth. And if you go along this diagonal, which is the pursuer rotation, so this is the self-play rotations. So if this diagonal is what's trained on. So the 0 versus 0, the 1 versus 1 pursuer, and the 2 versus 2 at that rotation. What you see is if we go this way, this is the pursuer rewards, our rewards get worse. So this is that the invader improves, but not necessarily as we go this way does the pursuer become better. We see these little dips where if the invader is really early, the pursuer seems to have lost something or forgotten something in those earlier invader actions that aren't letting it gain rewards or perform as good against that adversary. And then it's also helpful to see the invader's rewards in this game because it's not a symmetric game or in game theory, it's not a symmetric. The objectives aren't symmetric, but they're still competing. So we can see how the invader's rewards are affected by the pursuer learning. And we see it settles around 100. So within this region after we've trained for about 50 rotations. But before then, we cut it here. We see something that makes sense. The higher invaders do better against the lower pursuers or the lower rotation snapshot pursuers. But in general, the lower invaders who are usually more volatile, they're just kind of throwing themselves around, perform better against almost all of the pursuers that are trained. And that's probably because they will either hit walls or throw the pursuer into a wall. But now we have two privilege policies. We'll not worry about this too much. We'll move on to what we were talking about before, and we want to use this kind of realistic data to have this kind of baseline policy to use when we have only some limited information. So we've got these two policies, these two privilege policies from the self-play. What this will really only use is the privileged target spacecraft policy, but we still want to use the information we gain for the agent spacecraft and distill that into the unprivileged policy. Again, we talked about this in update 2. And the way we distill this is from this paper from UC Berkeley, where we use the KL divergence between the privileged policy and the unprivileged policy that's being trained to distill what has been learned in the privileged policy to the unprivileged policy and speed up its training. And we showed this last time as well. It does pretty well. It's still able to do it even with the unprivileged observations. But when we look at this, training plots, this is just for one, this is for lambda. First, I probably should have said, this is a kneel to 0 at half the total training steps. But when we do this, we see that when this lambda coefficient is non-zero, we learn really fast at the beginning, but once it hits 0, we actually drop. Okay, this is the length, but the rewards and the length are correlated. But once it hits 0, our rewards actually drop a lot, and then we start raising slowly. But over time, the entire training process, we are better than if we didn't have the term at all, which is this green curve. We tested it also for different lambda coefficients. They're also zeroed out at half the training time, and it's still kind of similar despite their magnitude being relatively separated. And then that was kind of where we ended off on update 2, and that was kind of the completion of what our motivation was and what our idea was. But if we look back at our inspiration, which is these kind of media YouTube channels, the AI Warehouse and Codeblock, who do like AI stuff and they make interesting graphics, we see that they both use Unity. So last weekend I took a shot at it and I made this. So these are our two agents, same game, but now he falls off because it's cooler if he falls off. nobody wants to see it hit a wall and end the game. But that's cool. But we'll look at it train. You can actually duplicate the environments as many times as you want. So here's as many as you can see. I just kept copy and pasting and spreading them out. But while it trains, I'll take any questions. Thank you for your time.
Okay, I'm Justin, this is Kelsey, and we're doing the reinforcement learning for control parameter tuning of an unmanned underwater vehicle. So going back to the project rationale, unmanned underwater vehicles, UUVs, are used in various
Application.
yeah, sorry, just blanked out there. So we focused on one specific model of UUV, so the Remus 100. So it's used in a lot of oceanographic science applications. And typically tuning the controllers for these units can take a lot of time and potentially money. So we wanted to explore some recent research looking at using reinforcement learning to make this process more efficient and also be able to cover control parameter tuning over various dynamics changes due to environmental changes that it might be operating in.
So just to recap what our RL setup was, so we have a fairly complex model of the Remus vehicle that includes hydrodynamics, actuator dynamics, rigid body, and hull dynamics. And then we also have drag damping factors in there. We also have a trim functions that initializes to a steady state so that we're not learning those dynamics as well. And then we also have noise on all of the sensed parameters to simulate a real vehicle. And then our gym environment, so our action space is the controller coefficients themselves. And then the observation space is all of the states of the vehicle as well as the controller errors that we're trying to minimize. And so it gets rewards for minimizing those errors and also penalties for large actuator motion. And then to reset, we're varying the water speed, the path that it's following, and then the lift and drag coefficients. And then it will terminate if it reaches a high pitch or roll angle, or if it reaches max time. And we'll talk about those more in depth because we played with all of those in the last few weeks.
So we found an issue about a week or week and a half ago. So we weren't actually passing the action values that the training was outputting into the dynamics model. So it was the base PID coefficients that were already part of the dynamic system that was being used consistently in training. So once we found this, well, we didn't find this issue out until we did some in-depth evaluation of our results and realized like, wow, this looks very similar from the base model, a little too similar. So we did some in-depth like code analysis and realized, yeah, we're not actually passing these action values in. So we're like, okay, what do we do next? So path forward obviously fixed that issue. And then we did a training run with our current reward setup at the time. And then we also did that with our original reward setup. None of the results look good. So we're like, okay, let's move to an incremental RL application, which we had discussed with Kyle, I think a couple of days before this. So what we did, we used our action space became ranges over and under the base PID coefficient. So the action space is just looking at what the baseline tune parameter is, and then like anywhere from 100% under or over. So we looked at 20% up to 100% over and under those base PID coefficients to see what kind of results we would get, and then completed training using this setup.
So during that time, we found a bunch of fun ways that the model will try to kill itself, which was a fun development. So when we did try those original reward values that we tried, project update 1 versus when we moved to a positive reward structure, both of those, it was not wanting to stay alive. And so we tried removing the pitch and roll criteria because that's what it was doing, is pitching up almost immediately to end the episode. It no longer tried to kill itself that way, but it just drifted out into space until it timed out in order to minimize the rewards. And then when we used the incremental action space, if we gave it plus or minus 100, because 0 as a KP and KI parameter was in that space, it would just set everything to 0 and then kill itself that way. And then we also tried, instead of giving it a percent range, just add, so stay away from 0, but just add to the KP and KI. And it also just continued to truncate with the pitch and roll criteria. So Yeah. We didn't have time to try any of those, more in depth beyond what we did by switching to the incremental, just due to time constraint. But we definitely want to reevaluate opening up that space more than just the percent incremental range again in the future.
And so here's an example of one of the training curves of the model that included that zero value and ended up killing itself to get a higher reward. So you can see the number of times the episode is truncated versus reaching that terminal state is like 120 versus like 2 or 3. So most of the time it's being truncated versus reaching that terminal state, although it's maintaining a relatively high reward. And then here's looking at the training runs of the models that didn't end up killing themselves. So these were all plus or minus 20%, 40%, 60%, and 80% of that base PID coefficient was the action space for these models. So you can see like these look pretty good. The standard deviation approaches 0, starts to converge there. Explain variance is a bit noisy, but the 80% run, the tan color there, oscillates around 0.8. It's also the highest episode reward mean, that plus or minus 80%. And then the clip fraction stabilizes as well as the number of steps increases.
So we did some pretty extensive evaluations still in all of these different configurations. So each of the different configurations, we ran a nominal, a high water current, low drag and high drag on the vehicle drag, and then low rudder coefficient, and then both high current and high drag at the same time. And then some of the results. So this is a violin plot of the errors. Just throughout the entire episode, and then for the manual, the 20%, 40%, 60%, 80%. You can see that their biggest improvement was on the pitch control, which probably tells us that our manually tuned had the most room for improvement in that zone for pitch control, whereas we might be able to get more improvement on these in a different KP-KI space. And then this is also just showing the KP-KI throughout one individual test run. One thing with moving this to real hardware, we likely don't want to be updating the KP and KI parameters this frequently, so every frame as it was trained to do. So that's something that we'd want to look into, just because of how active it is, and then how it's flattening out potentially on flatter portions of the record. The same thing, but for a high drag case.
So let's look at the training curve of that plus or minus 8%, which ended up being our best result. So you can see the reward reaches its peak relatively early and stabilizes there. The episodes that are reaching the terminal state is 3 to 4 times. The number of them is 3 or 4 times higher than the episodes that are being truncated due to timing out or reaching angular constraints. And then looking at the standard deviation converges on 0. Explain variance is oscillating around 0.8, and that clip fraction is stabilizing as well. And then the approximate KL doesn't necessarily seem to converge. So maybe the policy is still exploring a bit there, but.
So here's just some final results comparing an 80% nominal test case to our original train. So still there, you can see our best improvement is on pitch error, but you're also seeing some depth error improvement as well. And so you can see, well, I don't know why it's not running, but this is a GIF that should. Nope. Supposed to snake through, but yeah, that's okay. And then on the next slide, you can see here that the manual video pitch is a lot more active. Sorry, it's a little laggy. You can see that the blue dot is a lot more active for a similar actuator motion in the aft. And then this is just the time history. So again, you can see similar performance throughout while still minimizing the pitch error. So we're not changing a lot of the dynamics of the vehicle in order to achieve that lower pitch error. Same thing for a high drag case. So improved performance on the pitch error and a little bit different path that it's following. Yeah. Same thing, you'll see the blue dot be more active in pitch than the green. Yep. So here's our references, our full GitHub repository with our environment, the papers that we referenced originally, the FOSSIN model, and then all of our many plots.
And looking at our future work, so as Kelsey mentioned previously, probably investigating the solar policy changes. So rather than every time step within the simulation of the episode, like setting some threshold that the error has to be over before you look at even changing that PID coefficient. Looking at investigating the large actuator movements outside of training variations, then actually going back and trying to set up that full reinforcement learning implementation rather than just an incremental version that we went with for our final results. Maybe looking at energy usage and implementing that into a reward structure to compare the two versus the baseline model. And then, of course, like trying to get it working on actual hardware, and then maybe even adding like trajectory tracking controls, so just adding temporal constraints on the actual path that you're following. Any questions?
We're the drop-down navigation team, and this is our final presentation. I'm Will.
I'm John.
And the goal and motivation for this project is to navigate a drop drone released from a UAV at 1,000 meters to hit a desired location to extinguish a fire. The drop drone uses rotors or blade-like rotors that will provide a lateral steering mechanism but cannot provide vertical thrust. And it should, via sensors, learn how the environment is affecting it and change its position accordingly. And the motivation is, in the overall project, is to increase the efficiency of detecting and extinguishing wildfires while ensuring a safe operating environment for those who go. So here's a video that Dr. Sintis sent us of the actual. This was deployed right away, correct? Or
yeah. That's
okay.
And then I just thought about your research today, actually, like, so moving forward with this project very quickly. We have a team of like 40 people behind, and I don't know, we can talk about whether you guys want to participate in the deployment.
Okay, so here's some of the progress we've made throughout the semester. First, we started with the 2D environment that was not deployable, and the thrusting was allowed to thrust throughout the time horizon. In our second progress update, we still had a 2D environment, but we incorporated instantaneous deployment, and we also incorporated wind velocities and, in turn, the drag forces associated with them. And then for this final update, we migrated to a 3-dimensional environment. We had gradual deployment as seen in this figure. And the environment has varying wind conditions depending on which environment we're using. And we're thrusting after deploying to simulate the real drop drone. So here are some of our RL parameters and variables. Our observation space consists of position and velocity of the drop drone and the position of the goal, as well as the thrust XY and deployment. And the action space is the thrust XY and deployment. And we have the actions as part of the observation space because the past actions may influence the current ones. For example, if the deployment, if we know that it's already deployed, we don't want to deploy again. So these next three affected the training time. So number of environments simultaneously running, we had 100. Sim time is how frequently it updates the dynamics of the agent, and policy time is how frequent the action is taken. So for every 10 dynamical steps, 1 action is taken. And this helps a more efficient training. And so from last time, we still have the same reward function where it's a Gaussian shaped curve. And in this example, the initial X position on this graph is 100. So at that position, it's rewarded very little. And then as it approaches 0, or as it approaches the goal, it reaches its peak reward. And we played around with a few other regularization terms, specifically action rate and effort penalty. Action rate would smooth out the thrusting values, but we were not getting good results in terms of the overall goal of arriving at the target.
Yeah, and then some of the other things that we also tried for the reward function, one thing that we looked at was minimizing the difference between the velocity vector of the drone and the vector between its current position and the goal state to try and ensure that it was heading towards the goal at most of the time steps. And another thing that we looked at was the difference between the last time step and the current time step in terms of the position.
Okay, so to set up our environment, we like defined various parameters. The first one being our environment range. We made it large, which went from -100,000 to 100,000 in the X and Y directions, and from 0 to 1,500 in the vertical Z direction. So then we defined our drone's initial conditions, and for this, we made the drone's initial position randomized. That was from the ranges -2,000 to 2,000 in the X and Y. But for the height, the vertical height, it was always at a constant at 1,000 because the real drone is set to be dropped at around 1,000 meters. And then also the initial velocity, since the drone will be dropped from any UAV, it has velocities of 45 meters per second in the X and Y direction. And then the vertical descent should slow down to around 5 meters per second before reaching the goal. And then onto the goal, we have it set at a stationary point at our origin 000. This is because it makes more sense for our drone to vary in location and find the appropriate trajectory and magnitude of thrust to accurately land on that specific goal. And then we also defined a few variables for our drag equation, which includes the coefficient of drag, surface area, and air density, which helps us eventually solve for drag forces. So onto our dynamics. So our code models external forces, specifically the wind, drag, and the forces acting on the blade. So in our environment, we have it so that the winds are being applied in the X and Y direction, so the horizontal planes. And for every new environment, we have it so the wind speeds are randomly generated in ranges from -5 meters per second to +5 meters per second. Also, to solve for our drag force, we use the complex drag equation, which is based on the drone's relative velocity to the wind and two angular components. We only need two angular components in a 3D space because we can define the horizontal plane with one angle, which we named it XY, and the elevation angle Z. So if we use three angles, it just makes the calculations more redundant and just a bit more complex, which is unnecessary for us. And then so here is our dynamics code. So we start off by defining our double integrator dynamics. And then in this, we have all the forces and the drag that is being applied and calculated here. And as I mentioned, since we're using two angular components, we can calculate our effective coefficient of drag and effective area instead of dividing them into their individual components X, Y, and Z, because this method is a bit more robust in calculating the true realistic dynamics of their drone. So also on the right here, we have two matrices A and B, which represent our systems dynamics and the control inputs, which helps us integrate any forces such as thrust and gravity. And lastly, for this over here is our equation for the blade's force. And we have here so it integrates the P gain, which helps what's the word?
So proportional.
Yeah, proportional controller, yeah. And then it helps like stabilize the descent and also adjust so that it maintains the target speed.
Okay, so one of the big changes between last update and this final presentation is the gradual deployment of the blades and slowing down the drone itself. For this, we use a simple proportional controller that just tries to minimize the error between that set point velocity of -5 meters per second, and that gets us the gradual slowdown that we'll see in some of the graphs in a second. Okay, so this is a GIF from one of the final train policies that we ended up with. As you can see on the left, we have the drone's position in XYZ mapped with the starting point and the goal point. And then the middle graph shows the XY thrust over time. As you can see, the deployment happened around 10 to 12 seconds. And that's where it begins to thrust and take action. And then in the final graph on the right, that's our Z velocity versus time. So we can see the gradual slowdown to -5 meters per second.
So the yellow and green are the X and Y thrusts?
Yes. Okay. So we experienced a lot of difficulties in training and saw a lot of adverse behavior. And there was a few common behaviors that we noticed throughout most of our training. One of those was oscillatory behavior, which can be seen in the graph on the left. The drone would tend to shoot across the screen back and forth and never reach the goal position. And then in other cases, it would shoot off into infinity and try and reach the bounds of the environment. So with integrating this on actual hardware, there's a few anticipated challenges that we see coming with that. The policy and model robustness when compared to the real environment. If our model for the environment that we've used so far isn't accurate, there could be some problems that come with that. Some sensor accuracy and noise, and this is something that we could work on in continued training by inducing noise in the environment so that the policy is more robust to noise in the actual environment with the real sensors. And then the integration of the XY thrust control on actual hardware. Right now, it's assumed in our dynamics that whatever thrust is chosen by the policy is applied on the hardware, and then extrapolating outside of any ranges seen in the training environment. So some of our results and learnings. One of the main things that was positive out of our training was the parachute deploying at a safe and appropriate height. Early on in some of the trainings, we would see the parachute would choose not to deploy at all or deploy instantly and slowly float down to the ground. Our robustness is a little bit questionable in terms of like the broadness of the environment. A lot of the training, we limited our range just so that we could see more effective actions out of the policy. And then if we were to do this again, probably start off with more literature exploration on machine learning for flight control, see what's been done in the past and take some work from there. And then maybe look at using imitation learning or reinforcement learning for the flight controller parameters instead of direct reinforcement learning for the control of the drone itself.
All right, hello everyone, I'm Steven. I'm Mary. And we're going to be going over our final project update. And we're doing breadcrumbs learning for Play-Doh. So a quick overview of our timeline. We've completed 1, 2, and 3, but we did not get to fingernail RL grasping. I'll talk about that in a little bit, but we did manage to get the grasping down with RL. So just a little overview. Our goal is to use RL to leverage a complex contact geometry of the Play-Doh hand. And so it's supposed to mimic kind of the way a human hand works, kind of like round, soft geometry, and the fingernails as well. And some of the parameters that we have are listed observations, actions, rewards, penalties, and terminations, but we'll go into those a little bit more.
And so here's kind of where we are right now. We've managed to successfully grab the block and hold it in an orientation. And so this is in anticipation of stacking. And so later on, we'll talk a little bit more about kind of like precise grasping using just 2 fingers to pinch. But this is kind of showing that we can now grab onto the block, hold it in place. And so the next step would be to start stacking and then use that fine pinching to start stacking smaller and smaller objects. So I'll talk about our rewards real quick. So there's our kernel function that we use for some of our rewards. And something we've been playing with are tuning the weights and also standard deviation. And something that we realized pretty quickly is that depending on the standard deviation, you can see the blue one is a pretty sharp angle. If that happens, the robot actually does not learn the gradient. And so it gets really confused on whether or not it should do the action or how to do the action to get the reward. And so we kind of have to like tune it so that we initialize it on the gradient so that it kind of learns that if it goes towards that reward that we're giving it, it actually gets more reward as opposed to just being confused, not knowing what to do, and then doing all this like funky stuff. So some of the rewards we have are palm reach. This is basically promoting that the hand gets as close as possible to the object. We have object goal tracking, which is basically just tracking the location of the object and our target position where we want to have that object. And so in that video before, that was kind of like the point in space. And then we also have a reward for lifting the object, and we set this to be a binary reward. So either it lifts it above a minimum height and it gets a reward, or it doesn't. We try to use this kernel and see if it'll learn the gradient and kind of like pick it up slowly and get to that target position, but it did not do very well learning that gradient. So we switched it back to the binary.
Additionally, for the rewards, if you see we have fine inside of parentheses, it's because we in fact have 2 of each rewards for those, standard palm reach and a standard object goal tracking, and then also a fine palm reach and then a fine object goal tracking. This is so we could further reinforce precision and also further reinforce the training that it should reach a much more precise object position, I guess you could say. So if you see that the fine one has a much lower standard deviation, which gives us a lot steeper curve, but we aren't able to just immediately give it that standard deviation because once again, as Stephen said, if we're not on the curve, the training gets lost. So we're using the general reward to help promote it to go to that fine standard deviation curve.
Yeah. And then some of the penalties, we penalize ground slip. This is basically what we notice is it kind of likes to scoop because of the contact geometry. It realizes that it's just easier to try to get the fingers underneath the blocks. And so we penalize movement in the XY plane before it is actually off of the plane itself. We also penalize orientation error. So if it's not in the desired orientation, we try to penalize it so that it can get into that desired orientation for that stacking. It's kind of hard to stack a block when it's on its diagonal edge as opposed to on the flat edge. And then our action rates and joint velocities are really just promoting smoother and better movements for all these actions. It's really easy for the policy to learn jittery action because it can get more reward and kind of explore more of the space. But really when we get to the fine, small objects, we want to be very precise and kind of like minimize all that shakiness. And then for termination conditions, we have a timeout, obviously, a base radius to kind of also prevent that scooping motion. And so if it gets too close, it hits a singularity. And so we kind of want to kill it before it gets there. Outer radius, it also realizes if you lift it and you throw it, your lift reward kind of goes to infinity. And so we want to penalize that as well. We want it to maintain contact. And then object drop, this is an interesting one, and we'll go into that a little bit more. But basically, if it drops the object or kind of like takes it too far out of the range, we want to penalize that type of action. And then here you can see, basically, we managed to get the 2 fingers to pinch the object. And so the reason it's shaking right now, it's kind of hard to see, is because of the lift reward. It's actually balancing the Jenga block onto its diagonal edge because that gives it just a little bit of reward. And so we are able to get kind of like that fine pinch, fine grasp. But when we were doing this iteration, we needed some work on the lifting, getting that curriculum set up.
So these are the modifications we implemented for the video that we showed in the beginning. First, we implemented gravity compensation for the robotic arm because the reinforcement learning has a lot harder time training the arm when there's gravity that's invoked on the arm and the hand. So we turned that off, or we compensated for the gravity. We also set up more realistic workspace. Originally, when we first trained, we had the arm floating up 10 centimeters up above the plane, and we wanted to lower it down, but there was a lot of self-collision issues with that. So instead, we added a table, and that's where this object drop termination comes into play. So if the object falls off the table, then the scene will get terminated, and then it will restart. And then the third one we modified is pretty much we tuned the friction for the grasping interface to be more realistic. Isaac Sim, as we learned through this project, is not really good for manipulation tasks, and not many people do it for manipulation. It's more known from locomotion and stuff. So that's why when it comes to manipulation, more people use Mujoka, which is a different RL training. And we also tuned our motor games further. There's a lot of tuning involved to ensure that we can get optimal motor games. And we tried a new grasping technique, specifically promoting symmetry in the grasp. So if you saw in the first video, we switched from a Jenga block to a cube because there's a couple of reasons behind this. First one, if we promote grasping symmetry, it's easier to transfer from sim to real, and also we are able to fine tune some other parameters more efficiently instead of having to worry about the very fine pinching motions, because we care about the entire trajectory, not just the pinching. And also we modified the dropping termination to change its behavior, which you can see in here. Before we, yeah, you can take it.
So basically on the left, this is for terminating when the object is dropped. And so you can see when it starts, it drops the object a lot. And so it kind of goes down as it learns to not drop the object. But the result of that is it also learns to stop reaching for the object, because if it touches the object and it falls and it gets penalized or terminated in this case, it learns to just not touch the object, and everything's great. That obviously was not optimal for what we're trying to do. So we modified it to stop penalizing, but still kind of like change the way it learns.
And so when we change that, you can see the object, it takes a little bit longer for it to stop dropping the object, but you do see that that reach reward goes up because it learns that it's okay to drop the object as long as it learns to stop dropping it over time.
So we also did a lot of extensive experimentation. This is one reason why we couldn't get to fingernail grasping. We had to run over 200 different training runs just to get something that's close to what we had at the beginning, which is close to what we want, but it's not exactly what we want. So we did over 200 runs, and we're probably going to have to do more in the future to get it more optimized. We also tried a lot of different plans to do the RL training and to make it successful. At the end, our finalized plan, which pretty much where we presented the parameters that we're using, specifically the observation, action, termination conditions, penalties, rewards, etc., to refine the performance. And for future plans, first one would be to use the current policy and try to stack various objects on top of each other. So first would just be stacking one cube on top of another cube, then maybe trying to do 3, 4, 5, however much. And then we'll try to get to the fingernail-based grasping strategies and try to get it so RL can learn how to utilize his fingernails. After that, we'll start to transition and try to do sim to real transfer, which is going to be a lot of pain and effort on that. And another thing is, since our lab is getting another arm, an interesting topic that we could cover is bimanual manipulation for more complex and coordinated tasks, such as threading a string through a pin or something like that. And any questions? We just had some fun. I don't know, just had some fun with the hand. We wanted to see this shows like opposition of the thumb, and we wanted to see how fast it can go. This is like the bigger project is we're using a Maestro hand, which is a hand exoskeleton to control Play-Doh hand. So this is pretty much we tested this yesterday. Yeah.
So this is controlled by Maestro?
Yes. Mm-hmm. So if you can see it's getting controlled right now.
Have any similar papers just treated the end effector as like a point that can move through space? I mean, as long as you're not near any singularities, it shouldn't really.
Yeah, you could just do a very simple robotic arm. Like it's just, I don't know, I guess simple joints. Huh? Oh yeah, we also have we tried doing IK. I've successfully implemented IK, but unfortunately it's just kind of gets swept underneath the rug because trying to find the correct stuff to make this work just took a lot of time. I mean, if we had another week, I think we could have gone and figured it out. But like, it's just deadlines, and this has been very hectic with this RL training, just trying to get the hand to work. Because even with IK, if our hand was still struggling, it's just the hand itself is a very complex training thing to do.
So we did sign language for imitation learning for this hand. So just a quick overview of the overall things we accomplished. So we created an imitation learning framework for the humanoid hand. So in total, we made 36 imitations for numbers 0 through 9 and letters A through Z for each of those. We made the architecture for recording and playing back the imitations, and then we made an architecture in Unity and Ultraleap for generating servo values for the imitations about every 0.2 seconds. We also put a voice module for Jetson, or a Jetson voice module on the hand. So this added speech recognition, and we developed TDP communication between the hand's Jetson and C++. And a Docker container that runs the Jetson voice in Python. We also developed speech to calculation, speech to spelling functionality, where you give it a verbal command and it gives you back, you give it a verbal command of a calculation and it calculates the resulting number and then signs that. And also a spelling functionality where you tell it to spell a word and it signs out the letters of the word. And also a lot of work on the actual hardware of the hand. as we'll tell you in the challenges, a lot of different things went wrong with the physical part of the hand. Different springs got too loose. We had to retighten. Some of the servos had bugs we had to fix. And then, yeah, those are the.
When you say 36 imitations, you mean 36 gestures or what?
Yeah, so basically in Ultraleap, we like recorded out like what like an A is, what like a 0 is.
Yeah.
And then basically the way that it worked is that it outputted a stream of servo values.
Mm-hmm.
So there's 11 servos on this, the wrist, and then 2 for each of the fingers. Like there's one for the wiggle, how far it moves, and one for like how far it extends.
Yeah.
And there's like a stream of like 20 to 30 of those per imitation.
Yeah.
So we like recorded those in Ultraleap, and then sometimes had to tweak some of them to make sure that like some of the servos were moving like less or more.
And Ultraleap is a software that records joint trajectories or servo trajectories.
What our hand tracker is using, yeah.
Okay.
Yeah.
There's a hand tracker. Okay.
The camera.
That was like the same for last semester, where like you had like it was like mirroring the
motion thing.
Yeah.
Okay.
Yeah. And then this is
so recent accomplishments since last time, we have fully developed our language to letter conversion functionality. So now we can convert our speech into letters and have it sign that out. We've recorded imitations for all numbers and letters. There was a lot of jankiness with that. Sometimes our servos would mess up. We've made sure all of them are at least identifiably the numbers and letters they're supposed to be. And then we also developed a computer vision model for recognizing ASL poses. We trained that using TensorFlow and achieved 96% accuracy using a data set we found online that contains about, I think it was like 80,000 poses. Challenges, hardware sucks. We wanted a robotic arm initially, but it's quite expensive, and the challenges of building one ourselves is a bit out of scope for this class. We decided to focus on getting good software. In terms of hardware, this little red board here caught fire last night. We had to replace it. It completely burnt out. Thankfully, we had a second one because it takes 2 weeks to ship here.
it actually like caught on fire.
Yeah,
it was like
bright flame. Voice recognition was initially suboptimal, so we had to modify our implementation of that. We looked at Whisper, and that doesn't have live transcription apparently, so we still had to make do with what we had. The Ultraleap tracker itself has a lot of problems with finger occlusion. If there's a pose where the thumb is behind these 2 fingers, then it really can't track that, so it struggles. We've also had to modernize a lot of the code and just make it easier to experiment with, so that took a fair amount of time. But at the end of this, we had 2 models, one for 10 imitations for numbers, which supports basic mathematical operations, and also supports brackets, so we can do some complex math if our voice recognition recognizes the command. We also have 26 imitations for our letters. We can spell any word. There is a lot of issues due to the thumb. Some of the poses look pretty similar because it can't get quite in the right spot, but we did as best as we could.
All right, so first the calculation model. So we showed some of this last time, but essentially you give a calculation command, so like 12 plus 18, and then it converts that into 30, 30, and then you have the 2 control policies for 3 and 0 that it signs. So this is an example of that, that we're actually gonna, or that we took a video of. So basically, if you give it this command, it'll figure out what the answer is, 28, separate it into 2 and 8, and then send it to the imitations for 2 and 8. And then this is the results on the left. That's a GIF of it. We have that video too that will play really quickly.
You might not be able to hear the audio.
And hopefully the audio works. 12 plus 18 minus 2. That's that model, and then
sorry, for the 8, what do you do? Like
8 is this. 2 and 8. Yeah, okay. 8 is the middle.
So you have a way to have 10
yeah.
digits for 100.
Yeah. So we had those like 0, 1, 2, 3,
play it again?
4. Yeah, sure.
We're gonna do a live.
We
demo
also
of
are
this
gonna
as
do
well,
live.
so you can get that.
So, to the middle finger's the little.
Middle finger
is
specifically is kind of struggling right now, but
and then we have a live demo we can do if my laptop turns back on. Here we go. Okay. Okay. Reconnect to this. Two times 3 plus 5. Is 6 plus 5 is 11. Oh, okay. Well,
same command number as on the video for that.
okay. 12 plus 18 minus 2.
Detected the 2 as TO, not actual number 2.
12 plus 18 minus 2. There we go.
There we go.
Yeah, there we go. Okay. So that's one of them. The other model we had was the, I might go to the next one. Oh, shit. Okay. Is the spelling. So this is similar to the calculations, slightly different. So basically, we say spell and then a word. It separates the word into distinct letters, and then there's imitations for each of the letters.
So the letters are using American Sign Language?
Yeah.
Okay.
Yep. And then, yes, let me, here, actually, yeah, play that.
Another example for the word busy.
And I'll do this, yes, again. This has to, I have to reload the torch model. Yeah. Busy, try to do busy.
Yeah, busy.
Here. Yeah. On mute right now, just like wait a little bit, yeah. All right.
Spell busy.
U S Y. Why is this? Okay.
A very long word.
Yeah.
The longer the word, it
we tried to get them all to come back to neutral so that you can like see each letter, but yeah, it can do longer words.
Yeah.
Anybody knows American Sign Language?
Anyone want to speak with their hand?
Yeah.
Yeah. They say the words with the size and they come back and they do.
Yeah, so our final part here, we also wanted to kind of do something more in line with the spirit of the class. We trained a computer vision model that recognizes ASL that we could eventually integrate with the hand to speak with it by signing to it. So essentially the hand is split into 21 different landmarks. We use a package called MediaPipe, which is able to use our camera and place these landmarks onto our hand. We have a database of about 80,000 photos that we use for training. They're all labeled with ASL poses. And these poses or the landmarks are pre-processed in training and in active usage for every frame. The positions and distances are normalized in every frame about that bottom 0 point, so that regardless of your position in the frame or your distance from the frame, your hand will always be in relatively the same pose. They'll always look the same. And we compute the pairwise distance between all of the landmarks to use for training, which makes it quite fast. It's about 210 pairs. And we use a simple TensorFlow model that trains in about a minute with 96% accuracy. I have that here.
It shows.
You mean you're going to train it right now?
It's just running the pre-trains. Yeah.
Yeah, to run the, yeah. We don't have time to train it right now.
So it's able to get these signs pretty well. This one is A, C, D, E, F, forget G. I'm starting to forget the later ones. L.
That's why, yeah. I should just wait to get thumb in.
Thumb in. I.
Yeah, there we go.
I, and then J is like this, but if you.
It's hard to because some of the signs you have to like
J.
move them, like J is that.
So medium type automatically overlays that on your test, right?
Yeah, and then our model identifies the model or the landmarks.
It could be actually a real problem, right? It's like you have a hand, you put it in the middle of the table, and a dinner with the, people have different problems, right? And everybody can talk normal, and they can be part of the conversation.
We thought last class we talked in humanoid robotics, that one we talked about like Disney animatronics. We thought it might be cool if you could just sign to like a Disney princess or something and it signs back.
Yeah.
But it's a bit niche, but I think it's pretty cool. Future work. We want to obviously attach this to an arm so that way we can use the framework we built, sort objects, do all sorts of cool stuff, sign actual words because we need arms for that. We want to further refine the hand motion. This finger really sucks right now because it's made of TPU. There's a lot of friction in some of the fingers. It's not perfect. Ideally, we can develop some sort of speech to action model where we tell it a command like, hey, move this block, and then it tries to interpret the speech and actually do an action from that. We want to improve our Unity imitation recording because, as I said, the finger occlusion is quite a big problem for complex movement. And then maybe we could also integrate our algorithms and our speech with ChatGPT so that it can give you real responses and you can just ask it something and it'll sign you back. Yeah, are there any questions?
Spell busy. U S
Why is this? 2 times 3 plus 5. Times 3 plus 5. Just 6 plus 5 is 11.
Do the same command on the.
He's communicating with us.
12 plus 18 minus 2.
As TO, not actual number 2.
12 plus 18 minus 2.
There we go.
Yeah, there we go. Okay. So that's one of them. The other model we had was the, wait for the next one, is the spelling. So this is similar to calculations, slightly different. So basically, you say spell and then word, it separates the word into distinct letters, and then there's imitations for each of the letters.
So again, the letters are using American Sign Language?
Yeah.
Okay.
Yeah. And then
Spell Izzy.
So what is RMA? RMA is a newer algorithm that mostly contains two components, a base policy and an adaptation module, which combined allows for like quadruped robots and other legged robots to react to novel situations in a fraction of a second. And you can train pretty complex behaviors such as what you see here without just fully in simulation without preset trajectories or anything like that. So
I'll just go into a little more detail about what the the meat of the RMA algorithm is. In the first phase of training, you train along with your PPO algorithm. I'll train the policy. You train the environmental encoder, which takes your privileged observations from the simulator, runs them through a 3-layer MLP, and outputs a latent space representation of those observations. And then for the adaptation module, in order to relearn that latent space, rather than having the privileged observations, privileged information from the simulator, you take just the last some number of states and actions and use that to infer the state of the robot and what the ground is like and everything else that you would have had from those privileged observations. And to do that, we run it through a 3-layer MLP and add on a 2-layer convolutional neural network that will be able to find patterns in that state and action history and put it into that same latent space.
Cool. So the way we started with this is first we set up Isaac Sim. That took some time, and basically Isaac Sim is a robot simulator made by NVIDIA, which is helpful for robot learning. Well, you can set it up to do robot learning using Isaac Lab, which is built on top of Isaac Sim. And we set up a Boston Dynamics spot, the yellow robot dog, in the simulator. And then just got it to work with the default, just RL policy. And then we also figured out how to put the policy on hardware just to test out that we could. Then, can you go next slide, please?
Yes.
Oh, okay.
Oh, sorry. Yeah, just for for our implementation of RMA, we changed a few things from the baseline of the paper. We added a foot airtime variance reward. If you saw it in the video that was played earlier, a robot actually drags its feet across the ground quite a bit. So we wanted to make sure that wasn't happening. Well, foot airtime, we wanted to pick it up. Foot airtime variance, we want the steps to be symmetrical. We don't want the base of the robot to have a lot of motion. We kind of just want it to move smoothly, and motion being linearly and in orientation. And then we don't want to take really hard steps. We added a foot impact penalty as well. And then you want to.
Yes, yeah, sure. So as we mentioned, there's two phases to this. First, you train the robot in simulation with privileged observation. So what that means is in the simulator, you can give it a whole bunch of information that you won't have in real life, like a height map of the ground or how exactly values defining ground friction very exactly. You can also have foot impact force, like we say here. So first we train an RL policy basically with all this extra information. So that's the first step. If you go to the next slide. And this is how training looks for that step. So we start, that's like at the top is just the way it starts. And then after a bunch of training, you can get it to actually walk around all this rough terrain and even up some stairs. So that's how it looks. This is phase 1 with the privileged observations. And then in phase 2, and again, in this case, we're still doing it in simulation. In phase 2, basically, you take the policy you learned in phase 1, which is up here, and this policy is set up so that it spits out a variable, a latent variable called Z. And you use this Z to basically tell the robot how to move, right? So now in phase 2, what you actually do is you take away all the privileged information, and then you get another neural network to give you the same Z, but with less information. In this case, less information means you only have a record of use.
So this video down is with a predicted Z with a it's not with the
Right.
student.
Yeah.
the
Yes.
student policy, right?
Yeah, that's right. So it's been trained to match the privileged encoder.
So as you remember from last time, our first run at this sucked. When we tried to put it into hardware, it just tumbled and rolled over, which was really risky, which you definitely don't want to see on a road like Spa that starts at 20K and goes to like $100,000. And so that was from our first policy that we made with Mason, but then we decided from this that we needed to do a testing pipeline so that this wouldn't put the robot in danger. So from that, we kind of decided to like a little bit of sim-to-sim comparison, train Mason's policy on Isaac Sim, and then take that Onyx policy, put it on Bodied, and kind of start seeing what it does. And start seeing, okay, what's the environment in the simulation space? What are the graphs telling us, etc. And so
Bodied's another physics simulator, so we want to see if the one policy works.
Yes, exactly. And so, and then this is how it kind of turned out. Let's see. Didn't show the little video thing. There you go. And so this is like the end result of like the policy running on Bodied. And it looks really funny. There's like a lot of things with friction. We really tried tuning it best. Kyle gave us like a lot of really good tips, but this is as best as we could get it. TLDR, it walks. So what this tells us is, okay, like if it walks, then it's probably gonna walk in real life, right? And
it looks like it's very frictionless environment.
Right, and even though we increase the friction parameter on the ground and on the legs, it still looked kind of like that. So I'm not sure if like it's something else when like the Bodied scripts that we made.
You didn't run it on a rugged terrain. Right?
No, we only ran on this one, but we still adjusted those parameters.
We just wanted to verify the policy was getting observations in the correct order and it wasn't going to do any unexpected behaviors really.
Exactly. And so the end result's this. It looks kind of pretty. We get like a lot of graphs from that on like all the observation spaces that we care about, and we're like, okay, like it makes sense. If we get closer, it makes sense. Nothing unusual, so that means that we can move on and do more hardware stuff, which is this.
So then we moved on to testing on actual hardware once we had a verification that things were working. As you'll be able to see from this video, this policy opposite the robot that is very different from the base gate. Part of it is because we didn't use a symmetrical gate as one of our reward terms, and that I mean front left foot, back right foot at the same time, and vice versa. But it works. The Boston Dynamics SDK is pretty good for transfer of RL policies as long as you can edit the observation terms to be what we need to be from their SDK, because right now they output. You know, we had to create an action in state history from the robot. We had to order them in proper order and get them to our Onyx policy. That's able to run and actually form movements on real world hardware.
It runs better than Bodied.
Yeah.
So there's two things we're gonna do. You guys can go right. So first of all, I'm gonna ask a couple of questions here, and say goodbye. And another thing we're gonna do is we're gonna take a picture on the wall. So hopefully we can set up this camera.
But my poll here is, I guess, two questions, or maybe one. Did you expect that machine learning for controls and for dynamic systems was this way, or what's your feeling, right? Was it something like, oh well, I was expecting the class would be like this, or is any notes, anybody that wants to comment on? I never thought that whatever RL was capable of doing these things, or there were so many tools out there, or who wants to make a comment? Raise your hand. Yes, Fernando.
Surprised by just the complexity of the software that's involved in it. It's like if
Yeah.
I had Kyle for ICT,
Yeah.
it just would not have happened. And in general, just for robotics, whenever you want to implement some algorithm, if it's simple, like you have to learn sometimes some really complex.
Yeah, yeah,
Smash a bunch of stuff.
yeah.
A
So
lot of it is like it feels like an art even.
having a person that is an expert is hugely useful. Yeah. Anybody else wants to make any other comment of unexpected things, or or you saw in the class?
It's hard.
It's hard. It's hard. Yeah, yeah, yeah. I know. Maybe yeah. Other questions is things that you would like to change in the future. Spending more time in a particular topic, introducing new topics. Is it something you would like to see more, less? Yes, yes.
More application.
More application, more like hands-on coding, and yeah. Yeah. Well, we really, so this class started as a topics course. So at the beginning, everything was reading, and then and then I had to create I had to create the homework, right? So first year we had 2 homeworks, then 4 homeworks, then and so on and so forth. Yes.
So what the level like PyTorch and neural networks knowledge and all that was before coming to this class? I mean, I had done it for a little while, so
It's hard to know. Yeah.
That homeworks that were built upon that.
Yes.
Slowly and coded in a practical coding way.
Right.
Have been really helpful because the only coding homeworks we had were like you immediately got kind of thrown in the deep end.
You mean like homeworks that are more like to learn kind of the basics of ML coding?
We're just doing, we talk about MNIST towards the end of the class.
Yes.
Right.
And we did it very fast. Yes.
MNIST as a homework. Then I think that's a very difficult thing to do, but I think it could be very useful for like just learning the basics of how you make a PyTorch model.
Yeah. Okay. Note taken. Yes.
I feel like the course kind of suffers from all of us coming from very different backgrounds.
Yeah.
Like, I think there's an assumption that if you're signing up for machine learning for dynamics and controls,
Yeah.
you like know what a neural network is. You probably know what like backpropagation vaguely does.
Yeah.
Like, I think week 1, maybe this is aggressive, but starting with the PyTorch practicum would be chef's kiss.
Really? So
Yes.
would you ask the statistical the statistics the theory and just go, really? Oh man. But then nobody's gonna know anything about. Okay. Yeah, that I think I'm starting to get the feeling, and I'll reduce the theory on statistics in the future. Yeah. What is it?
You sometimes learn theory for application.
You learn the theory for application? Yeah, that's a good point. Okay, Amit.
I was going to say something, but I was just going to say that as much as I agree with the fact that I would probably want to and will look more into coding for neural networks and PyTorch, but I also think that maybe like the couple first weeks that you were going through, like as opposed to then, but I think the very first intro to the statistics, especially for someone who doesn't have the ML background, will be helpful. So like I didn't have the ML background before coming to the class, so I think if I was just exposed to neural networks from first so
I'm a little worried about just doing a course on apply ML with no statistics, but maybe we'll try to reduce it a little bit, or do it at a different pace. Yeah.
I totally agree that like
Yeah.
having maybe like a little more coding
Yeah.
homeworks on PyTorch
Yep.
would probably be.
Yeah.
Yeah,
Yeah, Fernando.
I also, it seems like based on my understanding of like the current state of the art, it's like a big mix of like controls and RL, like on top. And spending more time on continuous RL, I think would have been really useful because it feels like that's what a lot of
At least we got to spend some time because in previous years we didn't have continuous RL, but yeah, it is the plan to have more continuous RL, which is much more useful for controls, to be honest, much more in connection. And I like GPs are great for dynamics, and then we saw the project of Omid and Mohammed. That was a great. I'm glad that not everybody did RL, and some people did sort of more of the classical methods, because I think people have a tendency to think like neural networks are going to solve everything, right? And sometimes it's an overkill, right? But controls are going to get weird, right? Because the multimodality is going to happen. Right now we have a project in the lab where we're combining motion and voice at the same time, right? So you move, you talk about things, and that's kind of in control theory. It's kind of doesn't exist control theory for voice and image. You already had a hard time with pixels and movement, and now we have pixels, movement, IMU, and voice, and and then we're going to have now brain signals as well. And these are very unorthodox controls domains, but it is the new controls, right? That we should not avoid it. Any last comment? So thank you all. It has been the best cohort so far in the projects. The quality of the projects was outstanding. As soon as I have time, I'll compile a video, and I'll send individual videos to each of the groups so you guys can have it for showing to your friends and whatever. And then hopefully we'll put it out and have people enjoying the class. So thank you all. That's it. We're going to take a picture.